It is common to have plots with the probability of error in a digital communication system. Typically, these plots represent the probability of error as a function of the ratio between the mean energy per symbol and n0. In this video, we will see how it is possible to express the probabilities of error as a function of this ratio. In general, most of the expressions of the probability of error include terms like this one or this one. Typically, we have the Q function because the noise has a Gaussian distribution, and the arguments are typically half of a distance, maybe the minimum distance between symbols in the constellation, half of this distance divided by a square root of n0 halves, or in general, a given number divided by a square root of n0 halves. With straightforward calculations, just rearranging terms, it's possible to rewrite these terms as Q of a given factor times the square root of the ratio between ES and N0. For instance, if we have expressions like this one, the factor V is the ratio between the minimum distance and the square root of 2 and the square root of ES. And if we have expressions like this one, the factor V is written as the numerator that we have here times square root of 2 divided by the square root of the mean energy per symbol. Now we are going to plot the probability of error as a function of ES divided by N0 for two examples. And we are going to consider two examples of binary constellations, where the probability of error is given by half of the distance between the symbols, by Q evaluated at half of the distance between the symbols divided by a square root of N0 halves. Here we consider a one-dimensional constellation, case A, with two symbols with coordinates plus A and minus A respectively, and an orthogonal constellation with dimension now 2 and with coordinates A0 and 0A respectively. It is straightforward to see that the mean energy per symbol in the first constellation is A to the power 2, because the energy of a symbol is its square modulus, the addition of the square of the coordinates, and in both cases we have a to the square and minus a to the square is a squared, so the average is a squared. The same thing happens for the second constellation. The addition of the coordinates to the square for a0 and a1 is a to the power 2. With respect to the distances, the distance in the first constellation is 2 times a, while the distance for the second constellation is a square root of 2 times a. With these values, it's straightforward to compute the factor v for these two constellations. In the first case, we have the ratio between the distance and square root of 2 and square root of ES. In this case is square root of 2, and for the second constellation is 1. So, in the first case, we have that the probability of error is Q of argument square root of 2 times ES divided by N0, and in the second case, we have that the probability of error is just equal to Q evaluated at the square root of ES divided by N0. And now it is possible to plot the probability of error for these two constellations as a function of the ratio between ES and N0. In this case, the plot is in decibels. In some cases, the probability of error is plotted as a function of the mean energy per bit divided by N0 instead of the mean energy per symbol divided by N0. In this case, we only need to take into account that the mean energy per bit is the ratio between the mean energy per symbol and the number of bits per symbol in the constellation, and in this case, if we have the expressions written as a function of the ratio ES divided by N0, we only need to include an additional factor, a square root of the number of bits per symbol in the expressions to get the plot as a function of energy per bit divided by n0. It's relatively simple to move from ES to EB.